Hello everyone, welcome back. This week we were talking about the Lab 6. So we are working on the R type and the I type instructions. So first let's go to our website. And as usual, we have PDF files and slides and ISE. ISE is our project, so you can download it. So let's open the PDF. So this is the structure for the Lab 6. You see the difference between the Lab 6 and the Lab 5 as we add more modules, site extent, multiplier, and control unit. So the reason why we need this mux is determining the second input to the ALUs comes from the register or comes from the site extent. So if we want to use the R type instruction, we go to the top. And if we want to run the I type instruction, the number, intermediate number, comes from the site extent, is go to the second port. So the mux is decided is R type instruction or the I type instruction. And the control signal comes from the control unit, which is controlled by the opcode here. So based on this structure, we can support up to 6 instructions. It's a list on the next page of this PDF file. So we can support from the add to sub and I and sub I. Okay, let's see the details how to finish this. After you open the ISE projects, and this is the top module, and here is the definition for the site extent and 2-1 mux. And here is the signal you need to connect with this structure. Besides the opcode from RD, RS, RT, S out ALU is the output of ALU, C out is the ALU's carry out, RS data, RT data, control ALU source and the control ALU opcode is the output from the control unit. So from the Lab 6, all the signal comes from the control unit. Is start with the control underscore and then connect the name. So this is our little protocol, and the sign out and the mux out is the output of the site extent and the multiplier. So first instruction fetch part is the same with the Lab 5. We just grab the instruction and break down to 4 parts. And for instruction decode, so you see we added more module here as a control unit. So the opcode goes to the opcode port of the control unit, and the output ALU opcode is control ALU opcode as the output. ALU source is the control ALU source, and it goes to the mux. And the register is connected as usual instead of the so the sign extend part the input is the RT and the output is sign out. Sign out, and this signal will goes into the mux layer. So for execute part, besides the ALU, we add one more module is the mux. The ALU is connected the same as usual with the Lab 5, but instead of the second port. So originally we gave the RT data to the ALU, but this time we give the mux out. Is the output from the mux. And the mux definition is here. Input port is RT data, is for the R type instruction, and I type instruction, the second input is sign out. It comes from the sign extension port. The selection signal is coming from the control, and the output is the mux out. So exactly this have the structure we saw here. Okay, that is the top module, sort of memory, and the write back is not for this lab. So let's see the details for each one. First is to see the sign extent module. The sign extent module actually is just to duplicate the most significant bits. So from the RT we have 4 bits, So the most significant bit is the third one. So the output is 16 bits, but the input is only 4 bits. So we just duplicate the most significant bits for several times. It's just like this. If you like, you can Google how to use the for loop in HDL, and you can have the precise way to write this part. So that's the sign extent. How about the control? So the control unit, there's only one input, is opcode, and the several outputs. So for this lab, we only have two. One is control the ALU, the second one is control the mux. And here is we use the case statement in the VHDL. Based on the opcode, we give the different cases. So for here, I comment out the opcode and give you some hints, so which instruction it is. For the 0, the opcode 0, which means we get the 4 zeros. So I use the 1 hexadecimal number to present the 4 binary bits. So if opcode is 0, which means binary 0, 0, 0, 0, it is do the addition, and I know the opcode should be to 2 bits 0, 0 is doing the add for the ALU, and the source should be 0 because we choose the top way is for the R type instruction. The same thing for the sub and OR. And if I do want to do the add I, the opcode is 0, 0 is doing the addition for ALU, but for this time the source ALU source for the mux is to choose the second way, comes from the sign extent is 1. So the sub I is doing the ALU doing subtraction, and the source is 1. So that's how you control it. So you can see here we will do the extent for several instructions later on. So that's the so far right now we have. For the others is some case is not for this part indicate some you give some wrong number, so we give some default value is all zeros. So that's the control unit. Okay, that's the all the way you need to modify it for the sign extent and the control unit at the top. So later you have to finish the test bench. So this time for test bench is the table on the bottom for this document. You have to test these instructions and do the same thing for the lab 5. Translate it, give the break down the instruction for each part, and give the values of the registers from the wave. So let me show you what it looks like. Change the tab to the simulation and click the test bench and simulate the behavior module. Okay, we still need the register signal, so click on the left part. Okay, so let me move it a little bit to make it clear. So this second one is a register file, and we drag the signal. And as usual, we change it to the sign extent. Sorry, sign decimal number, and the first one is the instruction is hexadecimal. Okay, let's restart it and run it again, and change the size of the window. Okay, that's the old instruction we have, and here you can see. So that's the final results, the value for this. The signal we want to, the instruction we want to test is the second one is add I. So the add I is, we give the number 5 directly to the R2, add with R2, give it to the R3. So The second instruction is here, so we click here. So we read the R2's value is 2 and add number 5, which is 7, and give it to the R3. So you see the iType instruction right now is supported. So that's the final results. Give me the screenshot for the wave and the table as your lab reports. Okay, that's all for Lab 6. Good luck. See you next time.